We begin the procedure for the estimation of water infiltration into soils and their underlying porous media with a definition sketch of a soil moisture curve which is unique to each soil and underlying porous media type, characteristics, and geological setting. Theta S defines the fully saturated soil condition at a given depth, which is defined at an elevation of 0 meters, which is coincident with the water table elevation. Thus, the datum for this demonstration is in reference to the fully saturated conditions. As noted on the horizontal axis, there is no upper limit on the soil moisture content curve, as this value varies based upon the soil type. However, the absolute range of the horizontal axis varies between 0 and 1. Correspondingly, a maximum value is not assigned to the vertical elevation axis, as the distance to the water table can vary significantly from centimeters below the ground surface to several hundred meters, depending upon what the geological setting and climatic conditions are for a given region. The horizontal plateau on the soil moisture curve coincides with the top of the capillary fringe, whereby the soil moisture content below this elevation remains relatively close to the saturated conditions. The upward vertical trending portion of the soil moisture curve coincides with the initial moisture content that exists in the soil upon the day of testing, represented here as theta I. A range in soil moisture contents exists within the soil, referred to as the effective moisture content, and here denoted by theta E, which coincides with the interconnected pore spaces that contribute to draining and percolation. Over this range, the initial moisture content condition may exist depending upon the day of testing. Below the effective moisture content range exists a residual moisture content, here denoted as theta R, which represents the blocked, isolated, or dead-end pore spaces that do not contribute to the effective draining or percolation of the porous media. Further, the shape of the soil moisture curve will vary based upon the initial moisture conditions and recent infiltration/percolation past, yielding a notably nonlinear relationship. The ring infiltrometer test will emulate a precipitation event, whereby producing a saturated condition at the ground surface, and thus a condition of theta S, which will propagate vertically downward through the porous media, which is known as percolation. Although the specifics of the soil moisture curve will not be quantified using this testing method, the maximum rate of infiltration from the ground surface into the soil will be estimated, and how this rate varies with time quantified. This threshold and rate of infiltration is particularly relevant when partitioning a precipitation event in a hydrology investigation to determine the volume of water contributing to infiltration versus that of overland flow. It is worth noting that in most environments, a fully saturated soil profile from the ground surface to the water table will not be achieved over the period of the test. What is most important to evaluate is the percolation rate through the porous media, and thus the infiltration rate. Spatially, it is further noted that any particular soil moisture curve and quantification of the infiltration rates is only considered representative for a given geological setting, moisture conditions, land use conditions such as forested, agriculture, or terraformed, for example, topography and vegetative cover. A broad range in values and rates can exist within the same geological setting. Here we will investigate the infiltration characteristics of a small mesoscale location of approximately 20 centimeters in diameter. A ring infiltrometer test is conducted by advancing a circular metal column of known diameter vertically into the ground, and preferably to at least a minimum depth of the B horizon of the soil profile, in other words below the topsoil layer. A known volume of water is added to the cylinder, and the rate at which the water surface decreases from within the cylinder is measured at discrete time intervals, and thus an infiltration rate estimated. As the water percolates through the porous media, here it is assumed that a saturated moisture content is maintained at the leading edge of the downward propagating moisture front. However, central to the assumptions of employing this approach is that infiltration occurs in a vertically downward one-dimensional direction. However, arising from the three-dimensional geological environment, transverse dispersion of the moisture front occurs, which can result in an overestimation of the volume of water, contributing to a spatially one-dimensional infiltration assumption. This deficiency can be partially overcome by advancing a second metal cylinder within the first metal cylinder, known as a double ring infiltrometer. Here a known volume of water is added above the ground surface to the area between the rings, identified here as V1, and a separate volume added to the area within the inner cylinder, here identified as V2. In this test configuration, both the rates at which the water surface is decreased between the two cylinders and within the inner cylinder are measured at discrete time intervals and thus an infiltration rate estimated. The employment of the double ring infiltrometer technique allows the water that is displaced from between the inner and outer cylinders to compensate for the transverse dispersion within the porous media, while the volume of water displaced within the inner ring allows for percolation of the wetting front through the soil profile more closely to emulate the vertical one-dimensional flow field. Here we will begin the procedure by removing the sod from around the cylinder where the test will be conducted. Removal of the sod will allow the water percolation to be more represented by the primary porosity of the porous media rather than enhanced macropores created by existing roots, worm trails, or dead or rotting root pathways. It is noted here that these types of macropores can create notably enhanced pathways for infiltration to occur, which can capture a significantly larger volume of receiving precipitation than the underlying porous media. Here we have identified on the outer cylinder with a strip of black tape the depth to which the outer cylinder will be advanced into the ground. It is noted that the length of the cylinders can also be changed depending upon the depth of the organic layer and the depth of the test desired. The outer cylinder or ring is first advanced into the soil, followed by the inner cylinder or ring to the same elevation at the top of the outer cylinder, and finally adjusted for level. The setups presented to this point have demonstrated falling head tests. However, to improve the accuracy of the test and to better control variables, a constant head test would be preferred. This can easily be achieved by controlling and quantifying the volume of water added to each cylinder area to maintain a constant height within and between the cylinders. A constant head test will be achieved by marking coincident fill lines at the same elevation datum and maintaining the given water surface throughout the experiment. Then, volumes of water are dispensed into the two separate areas, between the rings, represented as V1, and within the inner ring, represented as V2, at discrete time intervals to determine the infiltration rate. All of the pertinent background information is included in the field form for specific site tests. Fill lines are marked with the Sharpie for the constant head elevation to be used in the experiment. The fill height is transferred via a tape measure measurement from the outer cylinder to the inner cylinder used in the experiment. The outer and inner diameters of the cylinders are measured, which will be used in the analysis to determine the planimetric areas of the inner ring column and between the two rings. One graduated cylinder here is identified by wrapping black tape around the graduated cylinder. Here the 1000 milliliter container. This will be the dedicated graduated cylinder for dispensing water between the cylinders, identified as volume 1. The other graduated cylinder, the unmarked 500 milliliter graduated cylinder, will be dedicated to dispensing water into the inner ring, identified as volume 2. This distinction ensures that the water being filled into the graduated cylinders and dispensed into the rings are properly accounted for throughout the experiment. The graduated cylinders are filled and quickly dispensed into the rings until the water levels have reached the fill lines denoted with the Sharpie, hence the constant head values. The initial fill volumes for V1 and V2 are observed and recorded in the field record. Here it is of note that the graduated cylinder dedicated for filling the inner ring, V2, had to be refilled 2 more times to reach the constant head fill line. Once the inner and outer rings have been filled to the constant head elevation identified by the Sharpie, the stopwatch is initiated and a test is thereby underway. During the beginning phases of the test, observations and top-ups of the cylinder rings to the constant head fill lines will be made at 2-minute intervals. After approximately 10 minutes, observations and top-ups will be taken on 5-minute and eventually 10-minute intervals. Then, after volumes of water have been dispensed into the 2 ring areas, hence volume 1 and volume 2 areas, the updated volumes observed on the graduated cylinders are recorded. At this point in the experiment, the most important procedure to maintain is the proper accounting for the top-up volumes to the graduated cylinders and the rings. Noted here in the field record, every time the graduated cylinders are filled, they are recorded as either plus 1,000 milliliters or plus 500 milliliter observations, which are separate volumes to any volumes of water being dispensed into the infiltration rings. Now that the infiltration test has concluded, we will complete the field investigation by advancing a shallow core to further characterize the soil horizons and collect specimens for laboratory analysis. The core should be obtained proximal to the location where the infiltration test is being conducted, but not too close such that the in situ moisture content of the soils is properly represented and not biased by the infiltration test. Usually within 3 to 5 meters away from the infiltration test is sufficient. A small diameter shallow core auger is advanced into the soil. The recovered sample is extruded and the core advancement depth measured directly in the hole, in this case referred to as the travel distance, and the auger advancement was 25 centimeters into the subsurface. The core auger was further advanced into the soil profile, here between 25 and 52 centimeters below ground surface, recovered and also extruded. The contact between the A horizon and the E horizon in this case was noted at the 32 centimeter below ground surface location. It is here noted that not all soils exhibit an E horizon. For this particular core, the lighter colored material, which is non-consolidated in nature, is identified as the E horizon. A third auger core was advanced between 52 and 70 centimeters below ground surface, which was the maximum distance the core could be physically advanced without mechanical means, such as a drill rig. The E horizon material was present to a depth of 68 centimeters below ground surface, and then presumably the B horizon began, which was composed of a highly cohesive clay till material to a maximum depth core of 70 centimeters. A sample of the E horizon was collected to conduct a grain size analysis of the media and to determine what the initial and saturated moisture contents were, which are required for various infiltration models. The sample bag is labeled with the ID number, date of sample, sample time, sample depth, and horizon classification, and the person's name collecting the field sample. It is noted that it is important that this sample be collected within the first few minutes of being extruded. If the sample were to remain exposed to the atmosphere for any appreciable length of time, the sample would begin to dry out and the in situ representation of the initial moisture content lost and misrepresented in the laboratory analysis. The color of the E horizon was also identified using the Munsell soil color charts. The Munsell soil color charts are a standardized color reference guide for geological media which can aid in the interpretation of soil origin and the general geochemistry characteristics. Here the E horizon was identified as a light 7/2 10YR color. Similar to the reasons for storing a sample quickly after recovery to evaluate existing moisture content, the color comparison should also be undertaken relatively soon after the sample is extruded. Drying of the sample in the atmosphere will lead to a change in the moisture content and also allow oxidation to occur, which can both lead to a color change of the soil horizon. To test for plasticity, a sample of the E horizon was attempted to be rolled into a 3/4 inch ball to undertake the 3/4 inch ball test to evaluate the cohesiveness of the media of interest. After forming a 3/4 inch ball of material between one's hands, one presses their thumb into the newly shaped ball. If the ball deforms without cracking, this is a field indication of plasticity. In this case, a ball was not even able to be formed, indicating the non-cohesive structure of the substrate. If a cohesive material was identified, other field tests such as the field ribbon test or 3mm pencil roll test could be further undertaken. Because the sample was non-cohesive, the standardized grain size chart was used in the back of the Munson soil color charts to field estimate the grain size. Here the media is visually identified as a very fine-grained silty sand to a sandy silt composition when compared to the grain size chart. Similar to the reasons previously mentioned for quickly storing a sample to capture the in situ moisture content in the laboratory evaluation and the color evaluation, the test for plasticity here should also be done relatively soon after the sample is extruded so that it does not dry out and bias the results. Lastly, an acid test was undertaken on the E-horizon to test for the presence of carbonates. Here, drops of 10% hydrochloric acid are dispensed onto the sample and the degree of effervescence or bubbling observed and interpreted. It is important to investigate the presence of carbonates in an infiltration study, as dissolution of carbonates may occur at the ground surface due to reactions with the atmospheric carbon dioxide, but may create a pan layer at some distance below the ground surface which would impede or could impede infiltration into the subsurface. The level of effervescence is related to the mineralogy of the soil and parent material. Vigorous and strong levels of effervescence, such as in diatoms or limestone-derived soils respectively, indicate a notably high presence of carbonates, which would also indicate a high pH of the soil horizon. In some soils, the level of effervescence is so weak that it may need to be observed with a magnifying glass. For this particular sample horizon, a moderate effervescence was observed. It is noted here that all of the field tests demonstrated could have been undertaken on each of the soil horizons identified in the core log, hence the A, E, and B horizons, albeit the B horizon would needed to have been advanced further. However, this instructional video was focusing in on the infiltration characteristics of the soil which were considered to be dictated for this particular coring example by the E horizon. Based upon the combined laboratory sieve and hydrometer analysis, the resulting grain size distribution from the sampled E-horizon is shown here, following the Unified Soil Classification System criteria. The media is characterized as a poorly graded sandy silt material, which is also shown on the trilinear diagram. The soil composition can also be interpreted on the USDA textural soil classification plot, utilizing the same grain size data for percentages of sand, silt, and clay, resulting in a silty loam designation. One final test will be compared here for classifying soils on the trilinear diagram by employing the jar shake test. Although this is an inadequate test from a geological engineering perspective to classify the grain size distribution of any given geological unit, if properly conducted, the test can provide a reasonable estimate of the general soil classification designation. Similar to a hydrometer test, the jar shake test is based upon Stokes' law, which relates the time of settling to various grain sizes. Here, a sample of soil was placed in a jar filled with water and vigorously shaken for 2 minutes. The jar was then placed on a workbench and the depth of settled material measured from the bottom of the jar after 10 seconds, 1 minute, 1 hour, and 24 hours. The thickness of each settled unit is measured and then used to estimate the percent sand, silt, and clay. From the jar shake test, the relative percentages of sand, silt, and clay are plotted on the trilinear diagrams, showing that the results of this test coincide with the soil classifications generated from the grain size and hydrometer analysis, although there were notable differences in the overall percentages. The final two items evaluated in the lab analysis were the initial and saturated soil moisture contents of the E-horizon. Theta I was determined to be 16.85%. This was determined by massing the collected E-horizon sample and then remassing it after drying in an oven. The difference in weight relative to the pre-dried weight is the initial moisture content. The saturated soil moisture content was determined by emptying the E-horizon sample into a permeability testing column and compacting it. A hydraulic gradient test was imposed across the compacted soil. When water flowed out of the bottom of the sample at the base of the column at a steady flow rate, the soil sample was removed and massed. This was considered the fully saturated moisture content. Then the sample was dried and remassed. The difference between the fully wet and dried sample conditions is representative of the saturated moisture content. Here it was found that theta S was 40.04%. Also, based upon the sieve and hydrometer analysis, the soil type classification originally identified in the field will be changed from an SM silty sand designation to an ML inorganic silts and very fine sands designation based upon the grain size analysis and the hydrometer analysis. We will now complete our double ring infiltrometer analysis by processing the field data. We will reveal some additional spreadsheet fields that will be used in the analysis. The surface areas between the infiltration rings and within the inner ring where volumes 1 and 2 were dispensed from the graduated cylinders are calculated. For the area between the inner and outer rings, one must remember to take the inside diameter of the outer ring and the outside diameter of the inner ring for proper calculation of the area. The area of the inner ring is merely based upon the particular inside diameter. It is noted here that even if the rings were slightly bent during their advancement into the soil, the overall surface area of the inner ring and between the rings remain unchanged even if they do not maintain their perfect circular shape. The time interval midpoint between sequential readings is calculated as shown here as the average between the sequential observation times. Although a given volume of water is dispensed into the rings at the end of an observation time interval, this is the volume of water that infiltrated into the ground between time observations, and thus a centrally weighted time interval is the most appropriate observation time for representing infiltration rates as a function of time. Here we will show various calculations for the inner ring volume. The procedure is the same for the calculations of the outer ring. Each time interval infiltration volume is calculated. This is the difference in the observed volumes measured between successive top-ups to the inner ring area. The only condition here is to differentiate whether the graduated cylinder had been filled to its maximum fill line between ring top-ups or had been dispensed from the volume of water remaining in the graduated cylinder from the previous top-up. We recall that the 500 milliliter graduated cylinder was used to fill the inner ring area. For example, here in the first ring top-up, the graduated cylinder had been filled to the 500 milliliter fill line prior to the inner ring being topped up. After the ring top-up, 250 milliliters of water remained in the graduated cylinder. Thus, the infiltration volume over the time interval from 0 to 2 minutes was 250 milliliters, or column K minus column L. For the second top-up of water to the inner ring, the graduated cylinder was not refilled, but rather drawn off the remaining water in the vessel. At 4 minutes after topping up the inner ring area, 120 milliliters of water remained in the graduated cylinder. Thus, the infiltration volume over the time interval from 2 minutes, 250 milliliters in the graduated cylinder, to 4 minutes, 120 milliliters in the graduated cylinder, was the difference between these observations being 130 milliliters, or column L of the previous observation time minus column L of the current observation time. This calculation sequence proceeds forward in time over each observation interval in a similar fashion. The infiltration rate in column N is determined by dividing the infiltration volumes that were just calculated in column M by the inner ring area of 167.42 centimeters squared. As 1 milliliter of water equates to 1 cubic centimeter of fluid volume, the resulting value is the per unit quantity of infiltrating water in centimeters. Multiplying this value by 10 converts the vertical quantity into millimeters. This product is then divided by the difference in sequential time observations as shown here to arrive at the infiltration rate in millimeters per minute. The same calculation is then made for each observation time over the duration of the experiment. The cumulative infiltration, column O, is the sequential sum of the infiltration per unit area observed values over the duration of the study. This is merely the infiltration volume at any given observation time, column M, divided by the inner ring area and multiplied by a factor of 10 to convert the value to millimeters. The calculated value is then added to the preceding value, with the initial value of the series beginning at 0 millimeters of infiltration as shown here. The calculations outlined here are repeated for those of the outer ring area. The only notable difference is now the area is adjusted to that between the inner and outer ring being 125 centimeters squared. We can then plot the results of the analysis. First, we will plot the infiltration rate versus experiment time of the inner ring observations, or what is considered the quasi-one-dimensional infiltration rate. Therefore, the infiltration rate, column N, is plotted against the midpoint of the time interval, column C, of the experiment. As observed, a decreasing infiltration rate is occurring with increasing time, which is nearing a steady-state condition. We can also apply a power law curve fit to the data and determine the infiltration relationship as a function of increasing time, as shown here. The cumulative infiltration can also be plotted by selecting the cumulative infiltration within the inner ring area, column O, against the observed time interval, column B in this case. It is noted here that the field observed time intervals are selected as the calculated cumulative infiltration rates coincides with the time of field observation. As we see from the plot, the cumulative infiltration is approaching a constant slope in later time, also suggesting that the field experiment is nearing a steady state condition. The infiltration rate of the area between the inner and outer rings can be evaluated by plotting column H against column C, the midpoint time interval. This result can be used to aid in interpreting how the subsurface flow field is behaving. In this case, the infiltration rate between the two rings as a function of time remains below the inner ring infiltration rate and is approaching a steady state condition. This is an indication that infiltration is behaving relatively well as a one-dimensional flow system. If, however, the infiltration rate of the outer ring area remained above that of the inner ring area or crossed the curve of the inner ring area, these would be indications that the larger volumes of infiltrating water were contributing to transverse dispersion and that the flow field could not be idealized as readily as a one-dimensional flow field. This concludes the demonstration of the double ring infiltration test. Thanks for coming to the field with us.